minus 1 a square, a square, a square. So everything is determined by the scale factor. So I'm using Cartesian coordinates, and I'm assuming the universe, the spatial curvature is 0. And this is the metric, and this simplifies a lot. It's not working?
Yeah, it's working, but you have to go in front of the first time. Back to you. Yeah, now it's working.
Okay. So, yes. And also, so this is an assumption, and that determines the left-hand side of the equation. The right-hand side of the equation is the energy momentum tensor, which, assuming a perfect fluid description, T mu nu is also diagonal. And the first component is the energy density, and the other components are the pressure of the system, of the fluid. So this is a fluid description of the stuff, matter radiation in the universe. Okay, so that's what we did. That's okay. Right. Yeah. Okay. So from this, we transform this this system of 10 partial differential equations, coupled partial differential equations, into 2 equations. And the equations are the Friedmann equations. So this is just a recap of yesterday, okay? So the first Friedmann equation which is the 0,0 component of Einstein's equation with these simplifications. So this is where you had to derive all the connections and, yes. What is the A square? Okay. Huh? Why we have A square here? It's because of the metric. The way I wrote T mu nu, it has the A square here because of the metric. So when you write T mu nu like that, then you get something, because you have to multiply by the inverse of the metric, then you get without the A square, if you remember. Good, thanks. Yeah. Okay, so yeah, I think I did that last time. Yeah. Any more questions? So the 0,0 so what you have to do, and this was the exercise, you plug in the metric and you get the left-hand side of this equation. Okay, and that was it's very tedious to do that. You probably noticed that how tedious it is, and it can be done automatically. So the first Friedmann equation comes from the 0,0 component, and it's very simple. So the 0,0 component of the energy momentum tensor is rho. So that's why it appears rho on the right-hand side. So what is rho? Is the total density of the universe. What is A? Is the scale factor of the universe. So this gives you an equation for the expansion rate of the universe. And the second Friedmann equation comes from analyzing the ij component of this system. And we derived it last time. So actually, I made a mistake last time. You probably didn't notice, because I didn't derive the equation because I was lazy. and was late. So I will do it now, because when you get the ij component, what you really get is the following. You get minus 2 a double dot over a minus a dot over a square is 8 pi g pressure. That's the equation you get. So what I didn't do last time is to substitute a dot over a square using the first Friedman equation. I didn't do it. So I wrote the result, and I wrote the wrong result. So please when you look at your notes yesterday, you notice that there is a mistake. So let's do this very quickly. So this is minus 2 a double dot over a minus, and a dot over a square is just 8 pi g over 3 rho. That equals p. Now, if you solve for a double dot over a, what you get is minus 4 pi g over 3, because there's a 2 here, rho plus 3p. So that's the correct equation. So the mistake I made is that I forgot the factor 3 here. So this is the second Friedman equation. So this is the first equation, second Friedman equation. So that's it. That's all we need to study the universe, the average universe, the background universe, the homogeneous universe. Okay, so let's continue now. So this is item 8, or section 8 of the lecture. So I want to use these equations to study how the density of the fluids, so how rho evolves with the scale factor. So how you have a fluid, and how does the density changes with the scale factor. Again, just to remind you that we can use different ways of parameterizing time. And one of the ways is the scale factor. The scale factor is like a clock in the universe too. So the scale factor, what is the scale factor today? 1. What is the scale factor at the beginning of the universe? 0. So between 0 and 1, that's the whole history of the universe in the scale factor. Yes.
So the acceleration of the scale factor is always related to the trace of the energy momentum tensor, right?
Yeah, yeah.
So if you have like electromagnetic field or another source,
It doesn't source acceleration.
okay.
Yeah. All right. So let's look at how the density of a fluid evolve with time. So that's what we're going to do is take the time derivative of the first Friedman equation. So if you take the time derivative of the first Friedman equation, so now you have to help me. So taking the time derivative of the left-hand side, what you get is 2 times a dot over a. And then you have to, again, take the derivative of this guy here. So that's a double dot over a minus a dot over a square. And then you have a dot. That's that. Is that correct? Good, thanks. Because I always make mistakes, okay? All mistakes I make are on purpose, by the way. You know that, right? All mistakes, including that. That was on purpose. So this is just 8 pi g over 3. And the time derivative of the energy density. Okay? Now this guy here, I can use, again, the two Friedman equations to write this term as, so the first term is minus 4 pi g over 3 rho plus 3p. And the second term is just minus 8 pi g over 3 rho. So this is the first term, comes from the second Friedman equation, and the second term comes from the first Friedman equation. Again, make sure I don't make any mistakes. So I can write this as 8 pi g over 3. And then I have two so I want to write as, yes. There's a 2 here, so I write, sorry, just to make this easier. So this is, how to write this? All right, let me do this first. So this is 8 pi g over 3. Let me do it 4 pi g over 3. This is 4 pi g over 3. So this is a minus sign. So this is rho plus 3p plus 2 rho. Again, make sure I don't make any sign mistakes. Yes? The unknown is how rho evolves as a function of A. We're going to consider A known at this point. Okay? And then we see how the density changes with the expansion of the universe. Okay. Is there any mistake here? So this is minus 4 pi g over 3. And 3 rho plus 3p. So this is 3 rho plus 3p. So far, so good? So this equation here becomes, there's a 2 here. So this equation becomes minus 8 pi g over 3, a dot over a equals, sorry, that multiplies 3 rho plus 3p equals 8 pi g over 3 rho dot. So I can cancel the 8 pi g over 3. And what I get is rho dot equals minus 3 a dot over a rho plus p. So this is an equation for the time evolution of the density as a function of a and rho and p. Did I make any mistakes? Maybe I did. Let me check. Okay, this is correct. So in order to determine the evolution of the density of a fluid in the universe, as you probably notice, I cannot solve this equation because I don't know one of the variables. There is rho, there is a, there is p. So I have to find, in order to solve this equation, I have to assume a relation between pressure and energy density. I have to assume this thing. And we know for a fluid what this thing is, okay? That's why I assume. So this is, you know what this is called? This is called the equation of state of the fluid. So this is a relation between pressure and energy density. So W is a function. It could be a function of space and time, whatever, but we're going to make an assumption that W is a constant. So this is called the equation of state. And the W is the equation of state parameter. So in this case, where there's an equation of state relating pressure and fluid, where there's an equation of state relating the pressure and the energy density of a fluid, you can write this equation as this. Simply 1 plus the equation of state times the energy density. Okay? Yes. So energy, that's a very good question. Is energy conserved in the universe? Why not? Because there's no time translation symmetry. Now, energy is not conserved, but we know exactly how energy changes. And this is given by this equation I'm going to derive. Also, you can derive this same equation by taking the conservation of the energy momentum tensor. Take the derivative, the covariant derivative of the energy momentum tensor equals to 0, you derive the same equations. So it may be a bit confusing, but yeah. Any more questions? Yes. I'm assuming it's a constant. Yeah, you can try to measure things, sure. So I'm going to tell you, because we know some fluid mechanics, right? So I'm going to tell you what W is in some fluids that we know. Right now I can tell you, right? So what is the equation of state for a gas of photons? Have you ever taken a course in statistical mechanics and studied relativistic gas? Huh? No, for a relativistic gas, it's not. 1/3, yes, very good. So for a relativistic gas, a relativistic fluid, if you do your statistical mechanics, you see that this is something you study, and you can derive this relation. Okay? So this is something we're going to use. Just an example. Very good. So let's assume now that W is a constant for the moment. And if W is a constant, I can write this equation in the following way. D rho is minus 3 dA over A, 1 plus W rho. So the mathematicians will kill me, but this is true. So this means that d rho over rho is minus 3, 1 plus W dA over A. So how does the energy density changes with the scale factor? Yes. As simple as that. That's how the energy density of a fluid with a constant equation of state changes with the scale factor. And the scale factor, again, is like a time, right? As the universe grows in time, the scale factor grows. If you go back in the past, the scale factor decreases. Okay, so this is like time. All right? Now, let me go here. So now you're going to see, take some examples. So first I want to leave you an exercise. I want to leave you an exercise. And the exercise is the following. Suppose that the equation of state is not a constant. But changes with time. Okay? It's an exercise. So suppose you have a fluid, but the equation of state changes with time. And how does it change with time? Oh, I don't know, but I give you a possibility. Okay? So let's say the equation of state is a constant plus something that changes with time. And it changes with time in this way. Okay? Then the exercise is to show that if the equation of state behaves like so, the energy density is proportional to exponential of 3 WA, A minus 1, A to the minus 3, 1 plus W0 WA. A is the scale factor. Omega 0 and omega A are constants. So omega 0 and omega A are constants. Now, you may find this strange, but this is a very common parameterization for the equation of state of what we call dark energy, which I'll talk later. And this is called, the CPL parameterization, which is just a Taylor expansion. But anyway, it's called CPL parameterization. If you look at the literature, Chevalier, Polarski, Linder parametrization. That's what is CPL. And this is used to parameterize dark energy, okay? Just for you to know. All right. So let's see how matter and radiation, how the density of matter and radiation changes in the universe. So this is 9. Matter and radiation in the universe. So we can broadly classify the fluids in the universe into two types. One that's non-relativistic and the other is relativistic. So two types of fluids. Non-relativistic fluids. So non-relativistic fluids, as the name indicates, is that the particles in the fluid are not moving at very large speeds, So the pressure is very small compared to the energy density. So what happens in non-relativistic fluids is that the pressure is very small compared to the energy density. So the energy density has you have to include the masses of the particles, for instance. And the masses are much larger than the momenta, for instance, of these particles. So in essence, what this means is that the equation of state is 0 for these fluids. And that's what we call matter. We call matter. Sometimes if you look at literature, you can find the word dust. So those are fluids with 0 equation of state. So the pressure is negligible. So what happens in this case? In this case, the energy density of this non-relativistic fluid, I can even write as NR for non-relativistic, goes as what? A to the minus 3. So do you guys have interpretation for this? Yeah. So it's like a particles in a box that is expanding. So the scale factor A is like a distance in the universe. It gives you a scaling of the distance. So it's like a box that is increasing with time. And then what happens to the density? It goes as you have particles inside the box. So what happens to the energy density? It goes like 1 over the volume. Right? You have these particles, and the box is just expanding. And the particles are the same. Does that make sense? Yeah, exactly. So it's like a gas of non-relativistic particles, but in expanding volume, right? So the volume is expanding with time. And the expansion of the volume is given by the scale factor. So 1 over A to the cube is like the volume of this box that's increasing with time. Does that make sense? So the other type of fluid is, of course, a relativistic fluid. And I just mentioned that for relativistic fluid, the pressure is 1/3 of the energy density, which means that the equation of state is 1/3. So what happens with the energy density of a fluid, a relativistic fluid? How does it change with the scale factor? A to the minus 4, because here, if you put 1/3, 1 plus 1/3 is 4/3, and here you have factor 3, so it goes like A to the minus 4. So how do we understand this? So it's like having a box with photons in an expanding universe, right? So if the box increases in size, the number of photons is the same. So the density of number of photons decreases as 1 over the volume again, the number density of photons. However, you have to remember this, that the photons have energy which is proportional to their wave number. And if the universe is expanding, the wave number, the photons is changing as well. And the photon energy is decreasing linearly with the scale factor. So this gives the extra factor of A in the relation between the energy density of photons and the scale factor. Okay? That makes sense? Very good. Yes. Yes, so you can have whatever you want. In principle, this is called warm dark matter. this thing, what you're saying. So this is what, I should say that. This is what characterizes what's called cold dark matter. So what you do, you actually have the expressions for the phase space distributions of these things, and you just integrate over phase space, and you get the relations between pressure and density. So I'm doing something very simplified here. Okay, more questions? Yes. What factor 1/3? Ah, here. So this thing comes from studying the statistical mechanics of a gas of relativistic particles. So you know what is the distribution of the energy of these particles? It's called Maxwell-Boltzmann distribution. And then you can compute the energy density for this gas of particles. You can compute the pressure of this gas of particles, and it comes out to be 1/3. So I didn't do it, and this is something I can either do it, or you can see in a course on statistical mechanics. You should see that. Thank you for the question. Any other questions? Very good. So we know how these two types of fluids change in the history of the universe. Now, we're talking about the universe, but when we talk about the universe, there's always an elephant in the room, as you know. You have asked me before about this. So what's the elephant in the room in cosmology? Is the cosmological constant. So finally, I'm going to talk about the cosmological constant, because I haven't done it yet. So I will show you that we can treat the cosmological constant as a fluid. It's a very strange fluid, but you can treat it as a fluid. So what is the cosmological constant? So what Einstein did, you can change the equations, Einstein's equations. So Einstein changed his own equations in 1917. So 1915 was the year where Einstein published his equations, the field equations of general relativity. And then he tried to apply it to the universe. And his conviction, based on experimental data at that time, is that the universe was static. And he applied his equations to the universe, and guess what? He found out the universe cannot be static. Why not? Because gravity is an attractive force. So in 1917, he introduced in his equations a constant that can be introduced because it doesn't change, is allowed by symmetries. And then you can write, so you can write an extra term, which is proportional to the metric, and it's a constant. R is not a constant, as you know, but lambda is a constant. So this term is allowed. It doesn't violate any symmetries. And he put this in order to have a static universe. And this is called the cosmological constant. So what we're going to do is, which for me is something more, many people, what is a cosmological constant? It's a property of space, in principle, right? It's something that permeates the whole space. But it's one way of looking at the cosmological constant is to make something very difficult, which is to put this term on the right-hand side of the equation. So I write Einstein's equation with the cosmological constant as this. Get the factors right. And an extra contribution to the energy momentum tensor, which comes from the cosmological constant. So what is this extra contribution? So I'm just putting the term, the cosmological constant term, on the left-hand side to the right-hand side, and write it as a T mu nu, as an energy momentum tensor. So what is this energy momentum tensor? So this energy momentum tensor, again, something very complicated to write. It's just lambda right? I didn't do anything, absolutely anything. I just wrote the cosmological constant term on the right-hand side and identified it as a energy momentum tensor. And I will define this as being minus rho lambda g mu nu. So I call this rho lambda. And this, in fact, will have units. I didn't talk much about units, but these units have to be the same as energy density. Okay? All right. So if I write like that, what is the 0, 0 component of this tensor? Rho lambda. What is the ij component of this tensor? Yes, a square rho lambda. Now, if you compare with a perfect fluid, yeah, it's negative, sorry. Yeah, actually, the way to do it, let me write like this. Maybe it's better to write like this, sorry. So this is just minus rho lambda Gij. Now there's no discussion about minus signs. Right? Now let's compare this with the energy momentum of a perfect fluid. For a perfect fluid, what is the energy? What is the 0, 0 component of perfect fluid? It's rho. Is the energy density of a perfect fluid. And if you look at your notes, what is the Ij component of a perfect fluid? P. Gij. So looking at these things, what do you conclude? That the cosmological constant is equivalent to an energy momentum tensor where the energy density of the cosmological constant is minus the pressure of the cosmological constant. So from this, you conclude that the energy density of a cosmological constant is minus the pressure of the cosmological constant. So what is the conclusion? The conclusion is that we can describe a cosmological constant as a perfect fluid, meaning a diagonal energy momentum tensor, with what equation of state? -1. So this means that the equation of state of this fluid, that is a description of the cosmological constant, is -1. Okay? Very good. Now we know that we can describe the cosmological constant as a perfect fluid with equation of state -1. What does it mean for the energy density of the cosmological constant? How does the energy density of the cosmological constant changes with time, or with this? It's constant. Remember that there was a -a to the -3, 1 plus w, but if w is -1, this goes like a to the power 0. So this is a constant. So that's, how do you interpret this? No, something that you expand your box and the energy density does not change. It's like the space in the box has energy. So you increase the box, you have more energy in the box. So that the ratio is constant. The ratio of this energy with the volume is constant. That's why this is called energy of the vacuum sometimes. It's energy of empty space. You can think of it as energy of empty space. So the energy density in the cosmological constant does not dilute. It's a constant with time. And now I can draw one of my favorite plots ever. Yes. Yes. Yes, you can put things that are R squared, things like that. So what you actually... so the cosmological constant, the way it's written, is a constant. Okay, so you have more complicated models. Then it's not a cosmological constant. So the way to look at this is, if you, I just mentioned briefly that these equations follow from an action, which is called the Einstein-Hilbert action. You can change the Einstein-Hilbert action by adding higher derivative terms. I mean, higher powers of R, for instance. But these are higher derivative terms, because remember, there are derivatives involved. And you have higher derivative terms. The equations of motion becomes higher order, and you can have instabilities. So it's not easy. Okay? Yes. Yes, yes. It goes by the name of f of R. Very creative name for putting a function of R in the in the Einstein-Hilbert action. Which, by the way, they're almost excluded observationally. So now I can plot what I think is one of my favorite graphs in cosmology. So what I plot here is time. But I'm not going to use time. I'm going to use the scale factor as a proxy of time. And I'm not going to plot the scale factor. I'm going to plot the logarithm of the scale factor. So I'm going to plot log of A. And here I'm going to plot the density. But I'm not going to plot the density. I'm going to plot the log of density. Why? Because you see that there are power laws everywhere, right? Okay, so let's start today. What is the value of log A today? 0. So 0 is today. And here we go in the past. So the scale factor decreases as we go to the past. So if the scale factor decreases, let's talk first about radiation. So what happens to radiation when the scale factor, the energy density of radiation when the scale factor decreases? Hmm? Yes, it increases as you go back in time. How does it increase? With the factor a to the minus 4. So if I plot log is a straight line with inclination 4, right? So I do it, I don't know if I'm doing correct, but I'm doing something like this. So this is radiation. I don't know. It goes like this. Oh, this is terrible. Okay, I don't know. Like that. So let's talk about matter. How does matter changes with time? It's less, right? So the inclination of the curve is smaller. It's minus 3. So I know that there's more matter than radiation today, so let me write radiation like this. Start today, and then go back in time. So what happens back in time? I don't know, something like this. Again, sorry, this is, I hope you understand. And then there's one more component, which is the cosmological constant. How does it change with time? It doesn't. So how do I draw this cosmological constant in this plot? It's just a horizontal line. It so happens that today, the energy density of the cosmological constant is larger than matter and radiation. How do we know that? Measurements. And then it's a constant. Sorry about this. Sorry about the drawing. It's a constant, okay? And you can see that there are interesting points in this plot. For instance, at this point here, this is the point, this is the instant in time where dark energy, or the cosmological constant, becomes dominant over matter. So I call this the scale factor of dark energy. Let me call it scale factor of lambda. And this is ln of lambda. So this is when this is the scale factor value when the cosmological constant becomes dominant. And what happens here? What happens at this point? Sorry? Exactly. So this is when there's an equality between the energy density of matter and the energy density of radiation. So let me call it this A equality. So that's the usual name that people give to this. Okay? So what happens in the early universe when you go back in time? Which is the dominant component? Radiation. And what happens to the energy density in the past? The energy density grows a lot. So the universe in the past was very dense because the energy density grows with time. And the energy density in radiation is proportional to the temperature to the 4th power. So if the energy density in radiation is very large, what happens to the temperature of the universe? It's very large. So the universe started in a hot, dense state in the past. Does it sound familiar? Big Bang Theory? So the universe was in a hot, dense state in the past. So this just follows from these very simple considerations, okay? All right. So let's see in more detail now how the expansion, how the scale factor really changes with time. So this is 11, the expansion history of the universe. So we see how the expansion rate of the universe, or the expansion, how the scale factor changes with time. How do we do that? Looking again at the first three-minute equation. So let's look again at the first three-minute equation. And the first three-minute equation is this. I will forget the factor of 8 pi g over 3. It's proportional to the energy density. Right? Now, okay, I can write this as this. Right? And let's suppose, let's see what do they do here. Yeah. So we know that the fluid, with a certain equation of state, the energy density is proportional to A to the minus 3, 1 plus the equation of state. We just derived that. So we will use this in this equation and see how we will solve this equation for the scale factor. Okay? So let's do that. So A dot over A is proportional to A to the minus 3 halves 1 plus W. Which means that dA of A to the minus 1, A to the 3 halves 1 plus W is proportional to dt. Do you agree with this? So I can solve this equation, right? So A, I just integrate on both sides. And then I see how A behaves as a function of time. So if I integrate on both sides, what do I get here? Plus A, yes, A minus 1 plus 1. So this is A minus 1 goes away. So what you get is A to the 3 halves 1 plus W is proportional to T, which means that the scale factor as a function of T is proportional to T to 2 over 3, 1 plus W. This is how the scale factor changes with time. So let's see what happens to non-relativistic particles. So if W equals 0, this guy goes like T to what power? If you're looking at non-relativistic particles, 2/3. This is for non-relativistic particles. And you have relativistic particles. This goes as 1/2. As simple as that. So now we can compute, we just did, how the scale factor changes with time. This is real time, okay? So it always increases with time. It grows faster when you are in what phase? In relativistic phase. Very good. There's only one problem in this derivation. Not one problem. There's no problem. So let's see now what happens. So this is a fluid, when the universe is dominated by a non-relativistic fluid. This is when the universe is dominated by a relativistic fluid. So what happens when the universe is dominated by a cosmological constant? So if the universe is dominated by a cosmological constant, which is the case now, actually, what happens to the expansion of the universe? Then what happens to A dot over A? If the universe is dominated by a constant, by a cosmological constant. It's a constant. So A dot over A is a constant, which I call age, now as a constant. And what's the solution to this equation? So if the universe is dominated by a cosmological constant, the scale factor changes exponentially. So it's an exponential expansion. So we are in a phase where the universe is expanding exponentially. And the exponential growth actually means that the universe is accelerating. So why? Because A double dot over A, for a cosmological constant, so this is general, minus 4 pi g over 3 rho plus 3p. But for a cosmological constant, remember, p is minus rho. So this is minus 3 rho, and this is rho. So this is 8 pi g over 3 rho, if I didn't make any mistake. Lambda. So if this is lambda now, lambda dominated, it means that the acceleration is positive. Positive. So the universe is accelerating today. And this is what was discovered in 1998 and led to a Nobel Prize in 2011. That the universe is not only expanding, the expansion is accelerated. So since my chair is sleeping, I can continue. Oh, he's not sleeping. I'm joking because he's my friend, of course. But you know, there's a trick that I ask questions. If they don't have questions, I continue. So do you have questions? Yes. No, you can ask questions, of course. Yes. Yes, I will repeat the questions. Right. So the question is why Einstein added the cosmological constant term in his equations. Is that you can show, I didn't show, but you can show that this, you know that gravity only attracts. The cosmological constant has the effect of repulsion. So the idea of Einstein, when he added the term, is that the two things could cancel each other in such a way that the universe would be static. That was the idea, okay? Of course, it didn't work. First of all, it's not stable. It was shown later that this situation is not stable. We make a perturbation, this thing goes away. So the cosmological constant was forgotten. And Einstein actually, there's, there's only one source of this historical thing, that Einstein mentioned that the introduction of the cosmological constant was his biggest mistake. And now we know that there is a cosmological constant, or something very, very similar to a cosmological constant. So yeah, so the cosmological constant came back. Well, it was forgotten for some time, and then it came back. Thanks. Yes. 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 There's something called singularity. Right. So we know because we know that the universe, so if we're negative, or we want to have positive energy density, that's one thing. But there could be something called anti-de Sitter solutions, where the universe would be contracting very fast. So we know that it's expanding, not contracting. Yes. So if you work in, can I say this? If you work in string theory, anti-de Sitter, this is not what we observe. I didn't say anything. In anti-de Sitter, yes. So the question is, how do we know up to when? So this is a question that requires you to know the model that describes the universe. So the answer is, if the model that describes the universe is based on a cosmological constant, this is going to go forever, and the universe will always be accelerating. Now, we don't know if this is the model, okay? So this is an assumption. Yes. You mean not on, we know the universe is expanding, you mean accelerating. Yes. So yes, but they're all similar to a cosmological constant in the sense that it has to be a vacuum energy. So the condition for acceleration, as you can see from this, is that the relation between the energy density and the pressure is that the equation of state must be smaller than minus 1/3. So any effective fluid that gives you this equation of state smaller than minus 1/3 is accelerating. And then there's a very interesting question. What happens if you have a fluid where the equation of state is smaller than -1? But this is something, I don't know if I'm going to talk about. This is called, how's it called? There's a singularity in the future. It's called the Big Rip model. But yeah. Yes. Yes. Sorry? That means that the space, empty space, has energy. So if you increase the space, you get more energy. So as we said that in the beginning of the lecture, energy is not conserved in the universe. Why energy is not conserved? Because you don't have a time translation symmetry. So there's no conservation of energy, and we know exactly how energy changes, and this is how energy changes. So why? So the question is whether it makes sense to make a cosmological constant that's not constant. But we know in the universe, because it is expanding, there's no conservation of energy. So things we do here now is different from the future. The metric is time dependent. So locally, if you're in a local region, you don't see this effect very prominently. What is the question? If it's necessary? So what we need, what we saw from observations is that the universe is accelerating. That's all we know about, okay? So what is causing the acceleration? We call it dark energy, but we really don't know what is dark energy. What is the simplest model for dark energy? The simplest model for dark energy is a cosmological constant. And in the model of a cosmological constant, the cosmological constant is constant. But it's a model. You can have other models where the cosmological constant, where it's not a cosmological constant. It's something that has an equation of state that changes with time. And this is exactly the exercise I gave you, where you have an equation of state that can change with time. This, remember that? I gave you an exercise where the equation of state is a function of the scale factor. This is exactly what is used today to have a model for dark energy that's not constant. Yes? Yes. Yes. Radiation, yes. Absolutely. So you can compute, for instance, the expansion rate, you mean Hubble, right? The Hubble is the expansion rate. So in the beginning of the universe, not the very early stages, what do you see from this plot? The radiation dominates. So you know that the scale factor is proportional to T to the 2/3. What happens to the Hubble, because Hubble is the expansion rate, right? Hubble is A dot over A. So if the scale factor goes as T to the 2/3, A dot is 2/3 of T of 2/3 minus 1. So you can do this, and what you get is something like this. Sorry, it's 1/2, right? It's radiation dominated. Sorry, it's radiation dominated. So A dot over A is 1 over 2T. So that's how the expansion rate changes with time in the early universe. I don't know if that was your question. What stage of the universe the expansion rate was the greatest? So the expansion rate is the greatest today because we're expanding exponentially. The expansion rate, right? But these things you can compute. You can compute everything from here. Yes.
You need to put like a cosmological constant or something else to get an accelerating universe. Isn't that a proof that general relativity doesn't work in large scales?
So again, general relativity is the left-hand side of Einstein's equation, let's say, and the right-hand side is the energy-momentum tensor. So I included the cosmological constant energy-momentum tensor part. And you can include other things in the energy-momentum component. For instance, there are models that can explain the acceleration of the universe, which is based on field theory. So introduce another field that is responsible for the accelerated expansion of the universe. This field is called quintessence, just a name, okay? But that's it. And then that's it. So GR is correct, and you have another component of the universe that's causing the acceleration. Now, you may say, oh, maybe there's another model of gravity, which is not Einstein, like F of R, someone mentioned F of R, that can explain the acceleration of the universe without invoking anything like dark energy or anything like that. It's just modification of gravity. Can that happen? And the answer is yes, F of R can do it, but it's very much constrained by observations. Okay? And it's not easy to change GR. As I said, if you change GR, how do you change general relativity? How would you like to change general relativity? How do you change the action? So you're not breaking like diffeomorphism symmetries and things like that. So you can introduce higher powers of R, the Ricci scalar, or powers of the Ricci tensor, or powers of the Riemann tensor. All these things are allowed. But every time you do that, you're introducing higher order derivatives in the action. And therefore, higher order derivatives in the equations of motion. And this leads to instabilities. So you have to be very careful. There's, how is it called? Strogradsky instabilities and things like that. So you have to be very careful when you do that. And we have no indication that GR is failing anywhere.
Well, I think that when you add extra powers of, let's say, the Ricci scalar, that will contribute in like high energy.
But again, you have higher order differential equations. You have to compute the equations of motion and see what happens, okay? You have instabilities. So what I'm saying is that it's not easy to modify general relativity.
Yeah, of course. Like for explaining the dark energy, you need like a low energy correction because the energy scales are just.
The energy scales are small, so it's difficult to change things at small energies too. Yes.
So we talked about how energy is not conserved.
Yes. Yes. So the momentum is also not conserved, and you know, think of a photon. The photon is propagating the universe, and the momentum of the photon is like the energy also, and the momentum is changing of the photon as well. So yeah, it's the same. Yes. Sorry, you can show that, think of a photon, something very simple, right? A photon has a momentum, but the momentum is given by the inverse of the wavelength, and the wavelength is changing, so. Yeah, matter, you can show that also momentum changes of matter. So if you start with some very fast moving particle, it will decay to the flow, the Hubble flow. And you can show that. I guess I cannot continue.
1 minute.
1 minute. I can continue for 1 minute. Yes, so now you don't have a minute. Oh, the Hubble flow, you remember the Hubble law? That the velocity or momentum, if you want, goes like, is proportional to the distance. That's called the Hubble flow. Yeah, you can say that it's a frame where if you look at distant galaxies, they all follow this frame. But you have to be a bit careful with that. Yeah, so I prefer. So if you measure the velocity of galaxies and you get the Hubble law, there are corrections that are due to peculiar motions, but if you look at very large distances, they follow the Hubble law or Hubble-Lemaître law, and that's what we call the Hubble flow. So the velocities all tend to be in the Hubble flow at large distances. Any more questions? Yes. Yes. Ah, sorry. So is the modulus of the tree momentum that changes? Yeah. Um, okay, I have to think some more about this, but I'm pretty sure it's not conserved. So I see. I can show how it changes, but. Right. So yeah, I have to think some more about this. I think some more about this. I don't know the answer. Thank you. Any other questions? Okay, so coffee break.